Hello, everyone. I'm going to talk about identifying short-term impactors with LSST. So the question we asked was, how effective is LSST at identifying Earth-impacting asteroids during their final approach to Earth? So we used one of the simulated LSST baselines which is available on their website. We used a synthetic impactor population that was generated by Steve, who happens to have a poster at PDC. We propagated the orbits and generated synthetic detections using a open source simulation software that we developed at JPL. And we post-processed these and passed them through JPL's Scout system, which you heard about from Davide, for computing impact probabilities. So the LSST is a 8.4 meter telescope that is currently under construction in Chile. It is nominally going to conduct a 10-year survey beginning in 2022. And during this time, it will take 2.4 million observations, each about 30 seconds long. So the scanning pattern is such that each field would typically be visited twice per night with an interval of 25 minutes. And inter-night revisits would typically happen every 2 days. So this is what the LSST camera looks like. So it is made up of 189 of those small squares that you see, small CCDs. Each one is 4K by 4K, so you have 3.2 gigapixels. There's the moon for scale. So the field of view is about 3.5 degrees wide. But it has all these gaps between the chips. So although the chip area is 10.5 degrees square, the total active area is 9.5 degrees square. So you get a fill factor of 91%. So when we implemented the field of view for our simulations, we implemented the boundary of that chip and discarded 9% of the observations to match the 91% fill factor. So there are two ways in which LSST will mainly discover near-Earth objects or impactors. The first one, which I'll call three-nighters, would be pairs of detections over 3 nights, over a span of about 1 month, within a span of about 1 month. So in this case, we assume that these detections can be linked to each other and the asteroid will be cataloged. If the asteroid gets too close to Earth, then it starts moving really fast in the sky and it starts trailing in each of the 30-second exposures. So each of these detections starts getting trailed. And so if you get 2 trails in 1 night, you can report that to the NEOCP and you can get follow-up observations. And so this would be the other way of detecting or discovering asteroid. So you can measure the trail ends of the trailed observations to get 4 points that can be reported to the NEOCP. The other main input for our simulations was the synthetic impactor population. This was generated, as I said, by Steve using the NEO model from Granvik et al. 2018. We used 2,700 impactors for this study. They had impact dates randomly spread between 2022 and 2032, which is when LSST would be operational. The impact points on Earth are also randomly distributed, as you can see in this figure. We used the same orbits essentially for different size bins in this analysis. It might have a slight effect, but not a very pronounced effect. And you can see Steve's poster if you want details on how these synthetic impactors were generated. So we passed the synthetic impactor population and the simulated LSST fields through the survey simulation tool that I talked about, which is available on GitHub, by the way, along with a lot of other auxiliary information, such as the camera field of view, the Earth orientation file, and other things, and got a list of detections of the asteroids. So we used this list of detections. This is what a sample output from the software looks like. So this is an LSST field And the blue dots are detections that the tool said was inside the field of view, and the red ones are outside the field of view. So we use these detections and post-process them to get the 3-nighters as well as the single-night trail pairs that I talked about. And for the 3-nighters, since we were only interested in the final approach to the Earth, we limited our search to 180 days before impact. And we assumed all these asteroids will, all these observations will be linked, and the asteroid will be cataloged. For the single night trail pairs, we used observations only within a month of impact. This is based on the length of time that we can predict impacts in the future. We only took observations that were trailed by about an arc second or more over the 30-second exposure, and made sure that both the nightly pairs were trailed. So getting to the results, so this figure shows the fraction of impactors that were detected in the simulation as a function of absolute magnitude. So for the really bright ones, less than h equals 22, almost all of them are detected. Oh, so the blue one, the blue curve, which overlaps the black curve here, shows the fraction detected as 3-nighters. The red curve shows the fraction detected as trail pairs, and the black curve is just the total fraction detected by both methods. So for the really bright ones, most of the ones that can be detected are detected below h of 22. As h gets larger, or absolute magnitude gets larger, it becomes fainter. It becomes harder to get detections over 3 nights of the asteroid, and so the fraction reduces. If you go beyond absolute magnitude of 28, it becomes more likely that the asteroid will be discovered by single night trail pairs instead of 3-nighters. And over absolute magnitude of 31, it just becomes difficult to detect anything. But there are way more of these smaller asteroids, the larger absolute magnitude ones, than the lower ones. So if you multiply each of the fractions in each of these size bins by the number of impactors expected per year, you can get a number of impactors detected by LSST per year, which is what this figure shows. So this is a cumulative plot of the number of impactors detected per year as a function of absolute magnitude. So if you take h of 32, that is the rightmost point, you get about 1 to 2 impactors with h less than 32, which corresponds to a size of about 1.5 meters per year. So if you want, you can look at the detection magnitudes. Most of the trail pairs are detected when they're really bright. So for h of 22, all of the detections had visual magnitudes of less than 16. So which means that this just shows that you can move from h equals 22 to h equals 30, and you will still detect the same number of objects. So we also looked at warning times for trail pairs. So this is a histogram of the warning times. This is the time between the second detection, the second trail, and the time of impact. So this is a histogram of those times. And you see that for h less than 29, you have warning times of more than a day for most of the asteroids. Whereas if you move over to h equals 33, the histograms get squeezed to the left and you have shorter warning times. So if you plot the median value of the warning times, you see that for until h equals 29, the median value is about 1.5 days. And yeah, as you go to smaller values or smaller asteroids, larger absolute magnitudes, the warning times of trail pairs becomes similar to the warning time of 3-nighters. So I'll leave you with the conclusions. The takeaway points from the study are LSST would detect an average of 1 to 2 impactors with sizes greater than 1.5 meters per year. Most of these detections would be through single night trail pairs. And the median warning time for these detections would be about a day and a half. Thank you.
Thank you. I have a quick question to ask. You showed a picture of the impact points on the Earth that was pretty much isotropic. Did you trace back the approach directions in space of the ones that were going to impact, and what do you find?
So there's some of that in Steve's poster. There's sky density plots of where you can
tend
observe.
to either come straight from the opposition point or from the sun. And the fact that LSST sees almost exactly 50% of them is because they're looking at about half the size, the opposition direction.
Yeah.
I just wondered, I didn't see the plot. I was hoping to see that. Any other questions? Anybody?
Nice workshop. No. Did have a question though. So you're assuming that the detection efficiency is, you can always detect, or if you got 3 tracklets, you can always link them, right?
Yeah.
But then did you look into, so that's fine when you're trying to figure out, which ones you're detecting, but when you're debiasing and going back, right, we know that the linking efficiency and stuff like that. Did you also guys look at using different filters? You took that into account in doing your debiasing, going back to find the 1 to 2 impactors per year, that the filters are not the same between each of the observations?
No, we didn't do that.
Okay, so it's going to be a little bit lower than the 1
Okay.
to 2 because they're not staying in the same filters, and so it depends on the which filter they're using.
Okay. Yeah, we didn't have a filter. I mean, we did compute we did correct for color, but we didn't have a dependence on different filters.
Okay. Yeah.
I think we're out of time.